Okay, welcome back. This is the Year 10 practice exam I was going through. I did part 1. Questions 1 to 7 took 42 minutes. Hopefully do the rest of it in another video, in the second video. Won't need 3 videos. Remember, this is physics for international GCSE, Edexcel. So this is the paper 1 for the physics, which also is used for the double award science students. So I put together a paper covering topics on forces, electricity, waves, and energy. And it doesn't include anything that is from paper 2. So all the paper 2 stuff has not been used if you're doing physics. Okay, so that's all the bits in bold if you look at the syllabus. Okay, so this will be a really useful program for students revising next year as well when they're in year 11 if they want to revise the first 4 units. Okay, so here's as far as we got to question 8, and it says a car is moving along a road. The car has an initial velocity which is u of 26 meters per second. So remember, we use S, U, V, A, and T, where u is the initial speed. The car then accelerates at 1.2 meters per second squared. So that's the acceleration. A is this value, and until it reaches a final velocity of 35 meters per second. So that's V. State the formula linking acceleration, change in velocity, and time taken. Well, acceleration is change in velocity over time taken. Algebraically, you could write that as final velocity v minus initial velocity u divided by time taken. So please don't use alternative symbols. Use the symbols which are used in your exam. If you put this in a triangle, the difference or the change in velocity in brackets would be at the top, and underneath you would have acceleration in time. So if you want to know the change in velocity, you could multiply the acceleration by the time taken. In this case, they've given us v and u, and they want you to calculate the time taken for the car to accelerate to 35 meters per second. So we know if you want t, you want v minus u over a. So I've basically changed the equation, which would be a equals v minus u over t, which is normally how you give it. Yes, should say a equals v. I've changed to t equals v minus u over a. Okay, so this is changing the subject to the time taken. So 35 minus 6, because final minus initial, divided by the rate of acceleration, which is 1.2 meters per second squared, which gives you a time to 2 significant figures of 7.5 seconds. Okay, they've given you the unit, so you don't get a mark for the unit. You get 1 for putting the numbers in, 1 for changing it around to making it t or the subject, and 1 for the answer being correct. Part B is about the Doppler effect. It says a radar speed gun is used to measure the speed of the moving car. So basically, here's the speed gun, there's the car. The radar speed gun emits radio waves, obviously towards the car. The moving car reflects the radio waves back to the detector on the gun. So it's got an emitter and a detector inside it. The detected radio waves have a different frequency from the emitted radio waves. So there's a change in frequency, yeah, from being emitted to being detected. This change in frequency, delta F means change in. This change in frequency is used to measure the speed of the moving car. And depending on how fast it's moving, the frequency will change by a certain amount. Explain this change in frequency. Well, it's due to the Doppler effect. If you just say that, you'll get 1 mark. Okay, so how do you get the other marks? There's 4 marks you need to get. So we'll have a look at the mark scheme. So we just done part A at the top. Now they want to give any of these 4. The frequency doesn't just change, it increases. So realizing it increases gives you 1 mark. Due to the Doppler effect, 2 marks. The idea that the car behaves as a source of reflected waves. So as long as you've mentioned that you know that the car creates the reflected waves. Okay, so you need to make sure you've clearly stated that the reflected wave fronts, yeah, become closer together. So when it hits the moving car, and the car's moving in the same direction as the waves which are coming back towards the detector, the wavefronts get squashed together, yes, bunched up, yeah. Now the diagram would help if you wanted to add it. So that means the wavelength effectively decreases when it's reflected off the car. Then they mention reflected, so you don't really get the mark for the reflected, but it's just that you've got the concept in your mind that the wavelength is getting squashed up closer together, wavelength decreases. So really these are the same marking point, verbalized differently. Okay, so that's why the frequency increases, because the wavelength decreases. Now the speed of the wave stays constant, so if the wavelength decreases, that means the frequency must increase, because the speed is constant for the type of wave. Okay, so these are the marking points that you need to put in. So if you're my students and you didn't manage to get many of these marks, try to copy down this term and go back to the textbook and read how they've explained it with the diagram. And for your notes, make sure you link it to the waves becoming bunched up together in front of the car. They'll get squashed, and behind the car, so if the car's moving that way, behind the car, they'll get spread out more. Okay, so it's like the wavelengths have got longer behind and shorter in front. Okay, so the wavelengths go down here and the wavelengths go up there, and they're inversely proportional to the frequency. So you see, you have to break down the science into logical points verbalized in English rather than in maths. Okay, so that's question 8. The next question is on waves, optics. This question is about light. Diagram 1 shows a light ray entering a glass prism. So here's the glass prism, yeah. So the light ray enters here at point A. It gets refracted towards the normal. I've drawn the normal, yeah, so this is a normal drawn at point A, so that's the entry point of the ray. It bends towards the normal, so this angle is bigger, I is bigger than R, okay? And 40 degrees is this angle there. So this is called the normal. Describe what happens to the light ray when it enters a prism. Well, the light ray bends, which direction? Towards the normal, okay? So bends, you could say refracts, okay, towards the normal. Now, we'll have a look at the mark scheme in a minute. And then state the name of the line XY. Well, XY is another normal, but this time at point B. So that when the light goes in at A, it then goes towards this point here, and you need to draw another normal. All angles are measured to the normal, and they're giving you this angle here, 40 degrees, and it's not drawn to the normal. So you know that this must be 50 degrees because it's a right angle triangle at B to the normal. Okay, so you're stating that as being to the normal. Now, let's have a look at the mark scheme for the first part. So the first part, they'll accept bends, refracts, or changes direction, or changes speed, or changes wavelength for the first mark. The second mark, then you need to say it refracts or bends towards the normal. Yeah? Why? Because it slows down. So if you say slow down, or because the wavelength decreases, these are alternative ways of getting the second mark. Yeah, so this is the first mark, and this is for the second mark. Additional detail. Okay, hope that helps. You can also stop the video and go back to this mark scheme because it explains the rest of this question. Okay, so if you want to understand it, the wavefronts are at right angles to the ray, so these would be wavefronts, and inside they get closer together, so the wavelength decreases inside. Yeah, and that's why they slow down, because remember V equals F lambda. if the wavelength goes down, the number of waves per second doesn't change, and this time that causes the speed to decrease. That's why they slow down. Okay, so inside the glass they'll be slower, the wavefronts will be squashed, and then same with the reflected ray there. Okay, so this is actually the next part of the next question on the next page. So we'll come back to that second diagram. But then it wants you to talk about, state the formula linking critical angle and the refractive index. That's n, the refractive index, and this is c. So the sine of the critical angle is always equal to 1 over the refractive index. So if you know the refractive index for the material, you can work out the critical angle. Well, here's exactly what they're doing. They say that the refractive index for glass in the prism is 1.6. So that's n. So we know this is 1.6. That means sine of c is 1 over 1.6. That means c is sine to the minus 1 of 0.625, which is what, if you put in the calculator, decimalize it, you will get that, and the inverse sine of 0.625 gives you an angle of 38.68. That's 4 significant figures, but we only have 2 significant figures in our data, so you should only give your answer to 2 significant figures, and that's how you get the 4 marks for this section. Okay, 1 for putting numbers in, 1 for doing the inverse sine, and 1 for quoting the answer to an acceptable number of significant figures. It then says, go back to diagram 1, complete diagram 1 by continuing the path of the light ray from point B. Well, the angle I at point B was 50 degrees, which is greater than the critical angle we just calculated, which is why they're doing this after you've worked out the critical angle. Okay, so if this angle, as you can see, I've shown you if that's 40, this angle coming in at B to the normal, yeah, is 50 degrees. So 50 is greater than 39, which is the critical angle. So if it's greater than the critical angle, you're going to get total internal reflection. Yeah, so it's going to bounce back, and this angle should be 50 degrees as well. Okay, I'm not sure I've drawn it perfectly, but if you are clearly showing that you know is reflecting at the same angle, that should give you the mark. So that diagram 1, completing it here, you're showing that the total internal reflection occurs inside the prism, and that the angle of reflection, because it's internally reflected, this means angle, is the same as the angle that it hits the normal at B. Okay, so that's your 2 marks for that. Continue. The question continues with the second diagram. Yeah, so diagram 2 shows a similar prism, looks like the same shape, but it's made from a different material. Yeah, different refractive index. The critical angle for the new material is 55 degrees. Remember that angle, if the angle goes in the same, and here is 40 degrees, this is still 50 degrees. This time, the angle here is smaller than the critical angle, so angle I, incident here, which was where it was called point B on the before, is now less than C, so it's not going to reflect, but it's going to refract. Yeah, but it's going to refract away from the normal, because when it goes from the denser material, glass or whatever it is, glass, for example, if it was glass, if it goes into the air, this angle here will be much bigger than the angle in there. Okay, and that's sine I over sine R. So that's a ray diagram, and for those of you who were asking me, I said you should always make sure you know how to draw ray diagrams, and don't forget to put the arrows to show the direction light is traveling in. So that's question 9. Question 10 is about forces and motion. You've got a driving force here in a van, and there's a force pulling it back. So what is that? Diagram 1 shows a van accelerating, so it's speeding up. That means the driving force must be bigger than the resistive force, which is going against the driving force. Another word for driving force is thrust, like an engine thrust. Okay, the horizontal force acting on the van are shown. Horizontal means, yeah, along the horizon. Force X opposes the motion of the van. State the name of the force. Well, you could put air resistance, drag, or you could just put friction, okay? Because air resistance is a type of friction, so they'll accept friction, okay? The resultant force, that means the difference between this and that, yeah, is 1500 newtons. So it's 2500 here, and the resultant force forwards, yeah, so this resultant force, Fr, is equal to 1500. If this is 2500, this must be reducing 2500 to make the resultant force 1500. So 1500 is the resultant force, it's the driving force forwards minus the resistive force X backwards. So it's 1500 equals 2500 minus X. That means X is 1000. Okay? And the unit seems to have been not come out in the photocopy for this page, but they've given it to you, so you won't lose it if you didn't put the units. The next part is now showing that something's changed. Diagram 2 shows the resultant force acting on the van while it's braking. When it brakes, this time the resultant force is backwards and it's kilonewtons. So they're seeing that you can change kilo by multiplying by 10 to the 3. Okay. State the formula linking force, mass, and acceleration. Well, that's Newton's second law. Force in newtons, not kilonewtons. Mass in kilograms. And acceleration in meters per second squared. So if you put it in triangle, I've done it for you just for the being helpful going through the answers, is F at the top. The mass of the van is 1900 kilograms, 1900 kilograms, so there's the mass. The force is backwards, yes, acting against the motion, slowing it down. Calculate the acceleration, so you want the acceleration. And the force is negative, so you can put the negative value in there. So it's 14,000 newtons divided by the mass, 1900, and you'll get a negative acceleration, which should go in here. So you should put minus 7.4, and the units meters per second squared. Okay, so you'll get one for putting the numbers in, one for the answer, and one for the unit. Okay, because this time they haven't given you the unit. Then it says at the bottom, the van was traveling at an initial speed, 18 meters per second. Remember, initial speed is u, before braking. So it was going at 18 meters per second. Then it started braking, and it came to rest. That means the final speed came to rest, means v equals 0 meters per second. Okay. Calculate the distance traveled. The distance is s. Okay, we want to know what is s, traveled by the van while it's braking. Assume that the acceleration remains constant, because these equations, which this time you have to use v squared equals u squared plus 2as, where s is the distance, these equations only are called the constant acceleration formulae. You can't do it if the acceleration keeps changing. The maths becomes too complicated for physics at GCSE level. Okay, so we know we're using v squared equals u squared. Now v is the final speed, which is 0, so make sure you put it on the left-hand side, equals u squared, which was 18 squared, plus 2 times 7.4, which is what we calculated. If you've made an error here and you use your incorrect value and you do the maths correctly here, they'll give you credit for your work. Okay, so we know everything apart from s, we know it ends up with 0. So basically 18 squared is 324. So, and this is 14.8s. So if this is 14.8s and negative, you can add 14.8s to both sides, and therefore you're adding 14.8s here, and it makes it 14.8s must equal 18 squared, which is 324, divided by, put s on its own, you change the subject to make it s, divide both sides by 14.8, and you'll get this, and the answer is 21.89, which again you only need to put to 2 significant figures, because all the data provided is 2 significant figures in these questions. Okay, hope that helps. It then says describe. So you've got to put more than just, not state, describe 2 factors that would increase the braking distance. Let's have a look at the mark scheme. because describing means you need to show that you've understood exactly what's going to increase the braking distance. Okay, so increasing the braking distance, you can have any of these. An increased mass, so you need to say increased mass of the van will increase the braking distance. Increased speed of the van, so you can't just put speed, you need to put increased speed. Okay, the more mass, the more speed, it makes it more difficult to brake, therefore it will increase the braking distance. Less friction, you need to make sure you've explained that if there's less friction on the road, example, the road may be wet or icy, so you can't just put condition of the road. What condition? You need to clarify it. Okay, idea of worn vehicle parts, example, tires and brakes. Why? Because it's going to be, again, less friction. Okay, so you need to put because there will be less friction. So you need to describe the condition. Yeah, and then they're also put if the van's traveling downhill, it will make it more difficult to brake because, of course, gravity will be acting against the brakes as well as the kinetic energy of the car that needs to be worked against. Okay, so I hope this makes it clear that when they say you must describe it. Yeah, so I think I need to go back and check that I wasn't too lenient with some of you when you answered your questions. Okay, so it's not enough just to put mass or speed. Increased mass, increased speed. Yes, less friction on the roads. Give an example, wet or icy conditions. Then it says, when the van is fully loaded, that means it's full of equipment or something, its mass increases to 2,500. I think before it was 1,500 kilograms. I'm not sure on the previous question. So this is the mass. And the force is still the same, the braking force. We know this from part 1. Part B, yes, so it's 14,000 newtons braking force. Calculate the time, so this has changed, so this and this will allow you to work out the acceleration. When it's fully loaded, it will be more difficult to slow down. And if you do that, the new acceleration using F equals ma would come to 14,000, again negative. It'll be a minus 5.6. So if you've got minus 5.6, you've worked out the new acceleration. I think before it could accelerate at minus 7.4. Okay, this time calculate time. So once you got that, you've got the acceleration. We know A, so this is A, we know. And then calculate time taken. So again, they want you to work out time. And this time, you're changing this equation to work out time, because they've said for it to come to fully to rest. So U must be 0, and initially it was going, U is 18, and V is 0. Finally, to bring the fully loaded van to rest, so V should be 0. Initially it would be 18, which is why I've put 0 minus 18 there. Okay, so it'll be minus 18 minus 5.6, so the minuses cancel out and give you a ratio of 3.2, and the units must be in seconds. Again, you only need 2 significant figures. Okay, hope that makes sense. So you're first using Newton's second law the same way as you did before, and then you're using the fact that the acceleration is now different, and you know A, you know V, you know U, you just don't know T, so you have to change the subject of the equation. Okay, once you get used to doing a number of these, you'll see there's only certain variations on these mathematical questions they can give you, and you become good at maths, and you'll be able to get a nice 15-mark question with most of the answers being quite quick. Now this one was probably the worst answered question, and it's about conduction, convection and radiation, which is thermal energy transfer. So a teacher makes a hot drink, yeah? He puts the drink in a cup designed to keep the drink hot. It's got a lid on it, plastic lid, yeah, shiny metal outer surface, and then it's got a shiny metal inner surface as well, and in between the two surfaces, the two metal surfaces, there's a vacuum. So this photograph and the cross-sectional diagram, which is this one, so the photograph and the cross-sectional diagram, both show the cup. The shiny surfaces, this is my notes for you to understand. Shiny surfaces reduce heat loss or thermal energy transfer by radiation. Yeah, so this is shiny surfaces reduces radiation heat transfer. Plastic lid reduces heat loss by convection and by conduction, because plastic is a poor conductor, and vacuum is a really poor conductor because there's no particles in there. So the vacuum reduces heat loss by conduction. If I'd just written this down, I'll automatically get 3 marks. Okay, I should imagine. So but you've got to change that and to make it the answer, which is 6 marks. So explain how the design of the cup that I just described to you keeps the drink hot. Yeah. Refer to methods of energy transfer. Okay, so how can thermal energy transfer? When we did this topic, we looked at heat as a separate part of this topic. Can be by conduction, which is from layers of atoms to layers of atoms. Convection, by air or liquid heated, becoming expanding and becoming less dense. And the third method, right underneath, is radiation, which is kind of infrared. And we looked at different surfaces that radiate more and radiate less. So that's to do with a shiny surface. So here is the mark scheme of the points that they will accept. Okay? So they will allow any idea that energy is trapped inside, but they're not allowing you to put heat is trapped inside, because heat is the whole topic. Yeah? You could say the hot drink has internal energy. Yeah? And that's more advanced than heat. So heat is the whole topic, and the transfer of thermal energy, yes, is what we're talking about. So cup slows down or stops energy transfer to the surroundings. Yeah? Well, I don't think it will stop it. Yeah? I think it will slow down the energy transfer to the surroundings. So that's 1 mark for just saying that generally. First of all, they're talking about conduction. Now remember when we looked at the diagram, the conduction in my notes was to do with the vacuum, yes, and the plastic lid, I said. Yeah, so poor conductors are the plastic lid and the vacuum between. Metal obviously is a good conductor, but because for the metal to conduct heat, it either has to go up this way through the plastic lid, which is an insulator, or it's got to go through the vacuum, and in the vacuum there are no particles for it to conduct through. So conduction is through particles. And if there are no particles, conduction is really slowed down. Yeah. And it can really only go through the plastic. So the vacuum contains no particles. That will get you a mark. And this reduces conduction through the sides. Yeah. Both sides. And the plastic lid is the only other place it can conduct through. And the plastic is also a poor conductor. So this is all the conduction. So just from talking about conduction, you can get 4 marks. Yeah, but it's a matter of being clear in how you communicate your understanding of energy transfer. And then convection, air is trapped in by the lid. So if you say imagine you've got the hot drink and it's filled up to that purple line. Yeah, so here's some air. Now the air is going to heat up by the hot drink, yes, but you can't get the air expanding and rising because it's a tight-fitting lid. So you're not going to get any convection currents being able to be set up. If there is, it'll be so small, it's in this tiny little layer. Yeah? So, and you can't go outside there, so the heat stays trapped underneath the lid by convection. So air is trapped by the lid, reducing or stopping or minimizing convection from the surface. Okay, so they allow reducing. Yeah. It also says to it stops evaporation as well, which is another way of heat loss. Okay, which we haven't discussed really when we did this topic. So then finally, relating to radiation, that's the shiny surfaces. And a lot of students that I read the papers of had written that shiny surfaces are good absorbers. Well, no, it's the opposite. Shiny surfaces are poor absorbers of heat. So first they don't absorb it, they reflect the heat back in. Yeah? The inner surface will reflect the heat back in. Yeah? So it's only the inner surface that will reflect the heat back in. They don't absorb much heat because of that. And the outer layer, the shiny surface, is a poor emitter. So if any heat does get to the outer layer, it's a poor emitter of heat or infrared radiation. So again, you're not putting, see, they haven't used the word heat. They're talking about radiation, conduction, or convection as the three modes of energy transfer. So this, both of these shiny surfaces reduce energy transfer by radiation. Okay, so that's the level of communication skills you require, and I realize that a lot of students are doing GCSE in English where English is not their mother tongue. Okay, but this is a level of academic English you need to get to be able to answer such questions. Okay, so that is question 11. And there's only one more question left. You'll be pleased to know. That's 6 marks. That's the most difficult 6 marks in the paper. And I did warn my students that this was coming, and you have to be able to explain, for example, how a thermos flask works. A student does an investigation, the final question, question 12. Student does an investigation to determine the current voltage graph for an unknown component, X. Okay? Now, we did this in class with my students. The student uses the following equipment. Component X, which is actually drawn in the diagram, is just an unknown component, so they haven't shown what it is. Cell, so you need to know what a cell is. A cell is a big line and a small line. The big line is the positive terminal, and the small line is the negative terminal. Now, they've said cell, so that's the cell. A battery is more than one cell, so separated by dotted lines, showing you could have multiple positives and negatives. So you're not meant to put a battery, but I think they've been a bit lenient in the mark scheme, and if that's the only mistake you've made, they may overlook it. Variable resistor is a resistor with an arrow going through it, so normal resistor would just be the rectangle. Ammeter should be a circle. Some people use rectangles. You shouldn't. You should use a circle. A voltmeter also should be a circle with a V inside it. Connecting wires are just what you connect the components with. So draw the circuit diagram to show how the student should set up the equipment. Imagine you've got your cell there, yeah, and then you want to be able to vary the amount of voltage and current. You put your variable resistor in series with it. You connect it to component X. So these are the connecting wires. So here's component X. When we did it, we did bulb and we did fixed resistor. And then you need to measure the current in the circuit. Yeah. So that's an ammeter, needs to go in the circuit. And the current can then go through there. You can vary how much current is going through there, through the component and back again to the cell. Okay. So if you got all of that, you will get one for having all the correct symbols, one for having the variable resistor in the circuit so you can vary the current, and one for having an ammeter in the correct place in the circuit in series with component X. So what about the voltmeter? Where does the voltmeter go? Well, the voltmeter always goes in last. If you've been taught properly, you need to say the voltmeter always goes in afterwards, because you want to know the voltmeter reading of the component that you're investigating. So you put the voltmeter, which comes with its own 2 connecting leads, and they're usually plugged in on top of the other leads which are in the circuit. So this is the main circuit, and you've got 1 mark for putting the voltmeter in correctly. Okay. So they then given you the data of the student's investigation, And you notice voltage is in volts and current is in milliamps. And when we did it, we had to use milliamps to make sure we got a good variation of current. Okay. Now you'll notice the current stays at 0 for a long time, so it should give you a clue as to which component it is. All right, and then finally, only at 0.5 volts, a tiny amount of current came in, and then as you went up from 0.5, they're going up in 0.1 volts at a time, yeah? And the current suddenly starts to increase at 0.5, 0.6, 0.7, and 0.8, where it shoots up. They want you to plot this data on the grid, and they want you to plot the current on the y-axis. They've told you, so if you do it wrong, you'll lose that mark. And then they give you a mark for choosing sensible scales. That means they want you to make sure your scale's easy to plot from. And they want the V on the x-axis. They want the axes labeled with the correct units, so it should be in milliamps and in volts. And they want accurate plotting. If your plotting is inaccurate, you will lose the marks. And finally, when you draw your curve of best fit, it needs to be drawn going through all the points. So some people were ignoring all of these zeros and they didn't bother plotting them, so they lost accuracy for plotting, they lost that mark, and they lost the curve of best fit if they only included these 4 points. Okay, so zeros are needed for this question. You can't just ignore them. So I've only drawn the scale. So the scale going up 0.2, 0.2 each time, so that's a sensible scale. And here they're going up in 20s, in milliamps, all the way to 140 at the top. So the top would be there, 140, yeah? The next one at 0.7 would be here, would be 33. So you see the 30, 32, 34, so you want it in between those two, 33. The third one, if I show you on here, this is the examiner's graph, 33, 0.6 is 8, and then 0.5 is 2. 0.6 is 8, whereas 10, so 8 is there, and 0.5 is, I said, 2. And then 0.4, and all the other ones, they're going up in 0.4s, you need to put these in. If you don't put those in, including the 0 value, you will not be able to draw your curve of best fit. Now, if it's a curve of best fit, you need it to go through as many points as possible and drawing it smoothly. Okay? And that's just a skill you've got to get used to. So I get the one for the curve of best fit. My plotting is definitely accurate. I've got the units on both scales with the correct and the scale is good on both. So I've got 4 marks, okay? And then state the name of this thing. It's a diode, okay? It could be an LED, a light emitting diode, or a diode. So that's, oh, I didn't show you the bottom. So that's how you do the final question in this, and this exam total is out of 111 marks. And at the end of year 11, paper 1 will be out of 110 marks normally, okay? So this is really good practice for your timing of the paper, yeah, and for being able to get used to the kind of mistakes that students make when they're new to GCSE. And of course, I'd like to say one more thing to the students who lack focus in class. Now it's time to get serious and to take every lesson where you're fully focused, because that lack of focus is not only affecting you, but it's affecting your friends. So if you get distracted when the teacher is explaining it to you, for example, let's have a look at the earlier questions. For example, when you had to do some vectors, the fact that so many students didn't know that you have to draw a vector, the length of the arrow is crucial, yeah? Or what were the other common mistakes that people were making in this paper? Not being able to know, for example, that you have to change the units if they give you kilonewtons or whatever. Where were they? Yes? So just flicking through the paper, make sure that you, again, equal size arrows for force diagrams. So force diagrams are a really easy way of gaining or losing marks, okay? Putting your answer to two significant figures, being able to describe things, 5 marks for this question. So description questions are very difficult, okay? I think that's it. So here it comes to the beginning of question 7, 150 kilovolts, 150,000 volts, yeah. Using standard form when you're doing your calculations, 150,000 volts, and making sure you can use standard form in your calculator. I had one student who was putting his answers constantly in fractions. Fractions can be used in maths, they cannot be used in physics. You must show the number of significant figures, and everything must be decimalized, okay? So those are the kind of skills that you need to develop. Changing the subject of equations, knowing what each letter stands for. You just need to have attention to detail. Another 4 marker for describing the change in velocity, where the waves get bunched up in front. Those are the things. Ray diagrams will come up commonly. Knowing how to use the equations, knowing how to do inverse sine. Some people knew the ratio, but then they hadn't worked out the angle on their calculator. These were the common mistakes. Measuring angles to the normal, always, yeah, knowing what it means. These are the kind of things you need to really get clear in your mind before you go into the exam. The direction being negative means a negative acceleration is a deceleration, slowing down. Yes, the most difficult equation is probably v squared equals u squared plus 2as. Make sure you practice that before your mock exams in January. This is now the end of year 10. Okay, so year 10 is teaching you what you need to be able to cover. Year 11, it gets serious, and you need to really keep your head down and focused all the way. How to draw circuit diagrams, knowing all of the circuit symbols. Yeah, it's your job to do the learning. Your teacher just introduces the subject to you. You then have to go and do the hard work. Okay, plotting graphs of the skills of science, knowing what an independent variable is, knowing what a dependent variable is, how to plan an experiment, how to control variables, all those things all add up to things that you can be asked in the exam. Anyway, I hope you found it useful. Make sure if you're one of my students, you go through it and correct all the things, add the detail in. Remember, we use purple pens to make the improvements. And use it as a good practice. So please give me a like if you enjoyed watching it on the video. Share it with any friends you have who are doing the same paper as you, and subscribe for more videos coming your way next year. Okay, see you in the next video, or see you at work. Bye for now.